So in this fun little problem, we have uranium-238. Initially, it's undergoing an alpha decay into thorium-234. And we're given the hint that we should consider these mass numbers here. So we can see that during an alpha decay, our mass number goes to our mass number minus 4. Now this minus 4 is because the helium nuclei here is taking away 4 of the nuclides. Okay, now once we've got the thorium-234, we've just looked at this one undergoing beta decay. So this undergoes beta decay to become protactinium-234. And we've got an electron released as well, and our neutrino, antineutrino. Okay, so in this case, the mass number started at 234 and it remains at 234 because this beta decay is not removing any of the nuclides. It's merely converting from a neutron into a proton plus an electron, or from a proton into a neutron plus an anti-electron. So during beta decay, A is constant, A being the mass number. So considering alpha and beta decay, the only way that we can change a mass number is by an amount 4. So this tells us that the final mass number equals to the initial mass number minus 4, and let's just call it n, but in this case our n is equal to number of alpha decays. Okay, so we know from our multiple choice options that our final mass number is 206 or 207 or 208 or 209. And we know that our initial mass number was 238. And then we've got minus 4n, and this n is the number of alpha decays, which means that it is an integer. So, an integer. So we just need to know which one of these is possible when we subtract this off. Okay, so let's try and get order of magnitude-ish. If we tried 10 beta decays, we'd be subtracting 40, and that would tell us that 238 minus 40 would lead us with 198, which is a bit too big, so we don't quite have 10 beta decays. Let's try 8 beta decays. So in this case, we're subtracting 4 times 8, which is 32. 238 minus 32 is 206, so that is possible. So that tells us that the one which we end up with has to have an atomic number of 206, so we end up with lead 206.